Now the technique here was one that may have been developed by Fermat, but which was certainly a favourite of his, for which reason I'll give it his name, to decompose a large or largest number into a pair of prime factors. But not just any decomposition, only those decompositions where those particular factors are quite intractable, where they're deeply ingrained within the number. Not the case where one of them is close to the surface, like one of the primes from 2 to 11 that you can quickly check for. No, it's when those numbers are close to the centre, to the square root of the number, that you would use this particular algorithm. The square root because that's as far as you need to go to find factors of a number. For instance, with 96, if I was to rattle through all the factors, not the prime decomposition, just the factors of it, I would start with 1, and that's a trivial case, and then just go through them in order. 2 goes in, so that's 2 times 48. 3 goes in, so that's 3 times 32. 4 goes in, so that'll be 4 times 24. 5 doesn't go in. 6 goes in, so that'll be 6 times 16. 7 doesn't. 8 goes in, that's 8 times 12. These pairs are getting closer together now. So the only numbers I've got left are 9, 10 and 11. Because by the time I get to 12, I've already got it on this side. I only need to go as far as the square root of 96, which is just under 10. So I've only got to go as far as 9 then. And I've reached it, 9 didn't go in, so those are the factors. So I'm looking for deeply ingrained factors, meaning factors that are quite close to the square root of n. So, deeply ingrained prime factors. That means close to root n. So before trying to find these ingrained prime factors, first of all pick off the easy surface ones. If you had something like 1353 to decompose into prime factors, before resorting to algorithm, I would just check quickly for the trivial ones, the ones that are sitting on the surface there, like 2, 3, 5, 7, 11. Those are the main ones. 7's a bit of a pest. Well, first of all, 2 doesn't go in, doesn't end in an even number. 3, well, the digits add up to 12, so 3 goes into it, so divide that by 3. That's going to go 4, 1 over, that's going to be 5, that's going to be 1. Next part, you can see that divides by 11. Those two numbers add to the middle. But in general, the technique for deciding if something divides by 11 is to add the alternate digits. And if the sum of the alternate digits have a difference which is a multiple of 11, so either 0, 11, 22 and so on, if the difference between the sums of the two sets of alternate digits is a multiple of 11, the number divides by 11. You probably recognise that pattern straight away, but you know, and there it is. 5 take away 5 is 0, so that must divide by 11. So that's going to be 4, remainder 1, so that's 41. And there you are, 41's prime, so I didn't need to use any special technique. I could pick off all the prime factors quite easily. So, the technique then, what is this algorithm that Fermat used to decompose numbers with these deeply ingrained prime factors? Well, I know the algorithm, I'm not sure of what the origin of it was, so I'm guessing at this part that I'm putting down, but the technique is the difference of two squares. But before that, I'm going to have to go through this derivation here that I'm guessing at. So that we have, if a and b are the factors, I'm going to write this down first of all. A plus b squared, square the first, twice the product, square the last. And a minus b squared, that's the sum and the difference of the factors, would be a squared minus 2ab plus b squared. So that if you were to subtract them, if you were to do a plus b squared minus a minus b squared, that would be this expression, take away that expression, those would subtract, and you'd be left with 4ab. And there you are, ab. That's the original number, n. If I just take that 4 across and divide. So I've got this then. That number should break down into this difference of two squares. There's a 4 to divide though, of course, because I'm going to have a quarter of each of those. A quarter of a plus b squared. Well, a quarter is a half squared, so you could pop that half inside. That would be the same as a plus b over 2 squared. And something like that would be a minus b over 2 squared. So we'd have n, which is the AB, would be a quarter of both of those, so popping the 2 inside, which gives me a plus b upon 2 squared minus a minus b upon 2 squared. Notice what that stands for as far as these factors are concerned. That's the average, the mean of the factors, adding and halving them. So you've got the mean value squared minus the difference between them, or half the difference between them squared. Now, difference of 2 squares, I'll just check that. I've got difference of 2 squares pattern would be the first, take away the second, that would be a plus b upon 2 minus the a minus b upon 2, multiplied by the sum of them, a plus b upon 2, a minus b upon 2. And of course that will add up to half of a, take away half of a, that disappears, leaving you with b upon 2 plus, that gives you a b times, and that's going to be an a plus a upon 2 times an a. So this difference does give you, the difference in those two squares does give you the original number. And that will be the technique for finding this then. You would start with a and b are the factors. If you take that, I'll put that down first, I'm using this line here. If you've got a plus b upon 2 squared minus the number, take the number across, that should result in this difference squared. Now, the algorithm would be, remember this works best for deeply ingrained. The closer these primes are together, the better this works. Because the closer those two primes are together, the smaller this remainder is, the difference between them. And the closer those two numbers get to the square root of n. So the technique here is, I start with some number squared, and I keep trying numbers there until I'm left with a square as a remainder. Now obviously this first part then, for that I'm going to try root n squared. Because if it was exactly root n squared, the remainder would be 0, which is a perfect square, but that means my number would actually have been the square of a prime number. But I'm going to try those numbers and then successive numbers after that. I'd start off with root n. When I say root n, I don't mean some decimal. That would be the integer above root n. You would try root n where root n squared is greater than or equal to n, and then go through, and this is the algorithm, and then if that doesn't work, if that doesn't produce a perfect square, and then go through successive ones. Until I get, and here is the test, and the test is I end up with a perfect square. The test is arrive at a perfect square. Well, what's that in action? Right, there's the engine for this algorithm. Right, let's switch it on and see what happens. Here's a number, 667. Now, I've already checked that for surface factors. There aren't any, so you can go straight in with this. Well, the first step would be, right, if I'm looking for two numbers that multiply to give 667, and I've not been able to find them using surface factors, I'm assuming they're quite close together. Notice also what this implies in here. The closer the numbers are together, the smaller this difference will be, so the smaller the remainder will be, so the faster you'll find the answer. It's when this difference here gets larger that you might have to go through several squares until you find a perfect square. Well, what happens with this? Well, first of all, what's the square root of that? Well, and we'll have to do this Fermat style, back in the 1600s, no calculators here. So 667, well, 625 is 25. So it's going to be something slightly bigger than that. So I'm going to try 26. So my first attempt is going to be 26 for the average, if you like, of these two factors. Well, we'll just check that. What is 26 squared? Various ways of doing that. Might just use the pattern for the square roots, making it as. I normally don't write all this out. But it'll be square the first, square the last, in the middle twice the product. So square the first, square the last, and twice the product means multiplying those two together with a factor of 10. So that'd be 12, 120, doubled 240. So that's going to give me 676. So my first part would be, my first test would be, for the numbers squared, I'm going to try 26. Remember, I don't know what a and b are. So what's 26 squared, take away 667? Is that a perfect square or not? Well, that came to 676. Take away the 667, There the difference is 9, so you've cracked it. There it is, 3 squared. You hit it straight away. That's going to imply that these numbers are fairly close together. Remember, that's the way this works. The closer these factors are together, the more deeply they're ingrained, the faster this decomposition here will wash them out. So rearranging that then says this: 667, take that over to that side, bring this over this side, was made from 26 squared minus 3 squared. Now I can employ the difference of 2 squares. So I've got 26 minus 3, 26 plus 3, so that means I've got 23 times 29. Notice it worked straight away, first time, because those numbers are very close together. In terms of primes, those numbers are close. Another one, maybe this time putting them slightly further apart. Here's one, 2747. What's the prime decomposition of this? Well, the first thing I'll need to do is, assuming that they're deeply ingrained, that they'll both be roughly equal to the square root of that. So what is the square root of that? Well, if I go in 100, I've got 27 times 100, so it's round about 27, that's 5 point something or other times 10 for the square root of 100, so 50 odd. I might try 52 for instance. Remember, there's no calculator here. So is it 52 squared? Remember, I want something that will exceed this. So 52 squared, if I quickly square that, so I've got 2,504, that's 10 doubled, well it's 100, 200, so I've got 2704, that's not big enough. Now one thing that you do need to use, using this algorithm, when they're further apart is, you have to go through it several times. If 26 hadn't resulted in a perfect square as a remainder, I'd have tried 27 squared. And if that hadn't have worked, I'd have tried 28 squared. And I'd have carried on that way until I eventually found one that would work. And it will work as long as you've taken out all the other factors and there's only 2 factors left. Because if there were actually 3 factors in there, this only works in pairs. That means one of them would have to stick onto the other one, pushing them even further apart, making it take longer. That's why you need to pick out all the surface ones first of all, so there's only 2 left. Anyway, where was I? Right. Since I need to go through successive squares, I'm not going to keep multiplying out successive ones, because if I know one square, there's a simple way to get the next square. If I know 52 squared and I want 53 squared, well, that will just be your 52 plus 1 squared, which will be the 52 squared I've already had, plus twice the product. That's just doubling this number, plus the 1 squared. So it's just double that number plus 1. So it'll be 104 plus 1. So it'll be plus 105. So if I know 52 squared, I add on double 52 plus 1, and I'll get the next one. And same with 53. If I want 54 squared, it'll be double 53 plus 1 onto it. So what was that? So 53 squared must have been that number plus that number, which is 2809. So over here then, so what am I saying for this then? I'm saying I'm going to try 53, because that's the first one that's bigger. So 53 squared is the square that's bigger than the first square, larger than that. Take away 2747. So take away 2747, that'll leave me 2, that leaves me 6, that leaves me 62. That's not a perfect square. So I'll try 54 squared then. Doesn't mean anything's going wrong, it just means these 2 prime factors aren't quite as close together as you'd have liked them to have been. Now if I do 54 squared, take away that. Well, if I know 53 squared, I can get 54 squared by adding on double 53 plus 1, by adding on 106 plus 1, by adding on 107. And if I add 107 onto that number, I'll be adding 107 onto the remainder. So all I need to do is add 107 onto the remainder to get my new remainder. So that means the new remainder is going to be 169. Bingo! 169, that's 13 squared. So I've done it. Just rearrange this then. 2747 will be 54 squared minus 13 squared. Pattern for the difference of 2 squares. So I've got 54 minus 13 times 54 plus 13. 54 take away 13 will be 41. 54 plus 13 is going to be 67. Right, a third example here. one where the factors are even further apart, so I'm going to have to go through this algorithm several more times. Well, the first step would be, what's the square root of 1003 approximately? Well, if you go in by 100, that's like 10 times 100. That's not to say that you can just use your calculator in a real example to do this, rather than plodding. It's still probably quicker, I'm not so sure in this case, than plodding through it after 11 by saying, oh, does it divide by 13? Does it divide by 17? Does it divide by 19? Does it divide by 23? And so on. You know, doing it by trial and error. It's quite a nice little technique. Well, step would be, if I split that into that, that's obviously 10 times. That's going to be 3.1 odds. So answer would probably be like 31 or 32. I think I'll try 32. Is it 32 squared? If, like in the last example, that turned out to be too little, well, I could still do my difference. It's just my difference would be a negative amount. And all I would have to do for that negative amount would be, again, just add on the difference of the squares until it went positive. So if this does turn out to be too little, then I'll just work with that because I know how to get 33 squared from that. Just add the difference onto the difference. So what is 32 squared? So square the first, 900, square the last, 4. Twice the product, well, 3 2s are 6. So that's 60 doubled is 120. So altogether I've got 1024. It is bigger anyway, so I've got that. So that then would give me 32 squared minus that would be, taking away the 1003, leaves me 21. And 21's no use. So that means I'll now try 33 squared minus it. Now, I don't need to work out 33 squared if I already know 32 squared, because 33 squared will just be 32 squared plus 2 lots of 32 plus 1, plus 64 plus 1 is 65. So just adding on 65 to that. That gives me 86. That's not a perfect square, so I'll go to 34 squared. Now the handy thing about going further is this, I don't need to say 2 of them because I know that the difference now will just be 67. Because if that was 2 32s in one, and that's 2 33s in one, and so on, it's only going to be a difference of 2 between them each time. So adding on 67 this time is going to give me, that's a 13 and a 15. And that's not a perfect square. When these numbers start to get larger, you'll know when some of them could or couldn't be perfect squares because there are certain digits at the end that you just don't get with square numbers. Well, I may as well just go through them here. Obviously, if a number ends in 0, its square will end in a 0. If a number ends in 1, its square will end in a 1. If it ends in 2, its square will end in a 4. If it's a 3, its square will end in a 9. If it's a 4, it'll be a 6. If it's a 5, it's a 5, and so on. I won't have to carry on down here. If it's a 6, it'll end in a 6, because that's 36. A 7 will give a 9. 8 8s are 64. 9 9s are 81, and then it just repeats itself. These are the only digits that you can get at the end of a square. The missing numbers are, there's no 2, there's no 3, there's no 7, and there's no 8. If a number ends in 2, 3, 7 or 8, then it's not a square. So I know it's not a square anyway, but it can't be a square if it ends in 3. So, that aside, back to this. 35 squared minus 1003. Well, 35 squared will just be, again, 2 more than that will be 69 onto that, 69 more than that, so the difference will be 69 more than that. Add that on, straight away I can see I've had it, because 9 and 3 is going to give a 2, and it can't end in a 2. That's so it's a 12, another 12, and another 1. So that was no use. So now I go to 36 squared. I know here you begin to think, is it worth it going through all of this? It doesn't actually take that long to go through that, but yes, I know if you had a calculator, 13 didn't work, 17, because I've only got to go as far as the square root. I've only got to go up to 30 odds. Anyway, A minus the 1003, well, that will be 2. Again onto that. Yes, 1 and 2 makes 3, so obviously that's not it yet. Then I try 37 squared, but I'm deliberately picked this one because they were so far apart. That'll be 73 onto it then. And that will give me a 6 at the end, then a 6, and 1 to carry is 3. 366, unfortunately doesn't work. 38 squared will be 75 more than that. Well, that's a 1, and that's going to make that a 4, and that's a 4, and there you are. That's 221 squared. Got there eventually. But that's the feature of this algorithm. It works best when these intractable little factors are close together. As they get further apart, one of them becomes more accessible because it becomes smaller. It becomes smaller and rises closer to the surface where you can get at it. But now we can finally write this. 1003 is 38 squared, just taking that over, reading it backwards, minus 21 squared, using the difference of two squares, 38 minus 21, and 38 plus 21, so the factorisation is going to be 17 times 59. And that's why it took so long. As a last example, try this one yourself. Find all the simple prime factors until you're left with some lump of a number you're not happy with, then employ Fermat's decomposition. So, hopefully what you'd have done is this. You'd have said, right, that ends in a 2, so it divides by 2. I can pick that one off. That'll be 3, 0, 2, 5, 1, 1. Now, obviously it doesn't divide by 2 anymore. Test for 3. Do the digits add up to a multiple of 3? 5 and 5 is 10 and 2 is 12. Divides by 3. So divide that by 3. 1, 0, and again 0, 8, but remainder 1, 3, 7. Doesn't divide by 2, does it divide by 3? Add them up. I've got 9, 12, 19. No, doesn't end in a 5, so it doesn't divide by 5. 7's the bogus one, because there is a way of testing for dividing by 7, but quite often it's just as quick just to go through it yourself. Or maybe I could leave 7 until I've checked the other obvious one, which is the 11. What about alternate digits? I've got 1 and 0 and 3 is 4. 8, 0 and 8 and 7 is 15. The difference between 4 and 15 is 11. It's a multiple of 11, so this must divide by 11. 11 into 100, that'll be 9. 99, 1 over. Into 18, that'll just be 11, so that'll be 7 over. Into 73, that'll be 6. 66, leave 7 over. And then I've got, goes 7. Now I could test for that 7. I've got 1, 3, and then obviously 7 doesn't go into 67, so that's it. So this is the one I'm stuck with. I'm stuck with 9167. What goes into that? That's where I'll use this decomposition then. So the first step would be, what's the square root of 9167, just roughly? Well, that would be 91 times 100. The square root of 91 is 9 something, about 9.5, maybe 95. Putting that end back on, 95, 96. So try one of them. Well, 95 I know 95 straight off, because 95's got that simple pattern, because that ends in 25, and then it starts with 9 times the number after it, so it's 9025. So it's not 95 squared, because that's too little, so it's 96 squared I want. So I want, what's 96 squared minus 9167? Well, if I know 95 squared, I can get 96 squared by adding on 2 lots of 95 plus 1, by adding on 191. So that's going to give me 6129. Then take away the 9167, and I've got 9, and then 4, and that's it, 49. That comes to 49. Bingo! Perfect square, that's 7 squared. Then just rearrange it. So 9167 equals 96 squared minus 7 squared. Difference of two squares. 96 minus 7, 96 plus 7. So that's going to be 89 times 103. So finally, 605022 in its prime decomposition would be 2 times 3 times 11 times 89 times 103, all without a calculator. There you go. Courtesy of, we think, Pierre de Fermat. Same one you probably think of when you think of Fermat's last theorem.